Alright, so the point of this video is to show you how to do multiple linear regression in SPSS. So it's very similar to doing simple linear regression, only as you know now, with multiple linear regression we have multiple predictors, independent variables, covariates, so forth and so on that are being added. So for this example, we're going to be looking at the hemoglobin change data set, which I've already imported here into SPSS. And what I'm going to do is control for a number of covariates and assess the independent variable water. So to do multiple linear regression, you go to Analyze, go down to Regression, you go to Linear, and the first thing you do, you put in your dependent variable, just like with simple linear regression, which is change for this example. And then put in your independent variables. So I have my baseline hemoglobin change, my weight gain during pregnancy, my age, and the water variable. So this is how much tap water they drink. I want to make sure we have that in there. So I've got 4 independent variables, which really 3 of these are what I would consider covariates. They covary with the response, but they're not the main variable of interest. The main variable of interest is water. Then what we're going to want to do is go down through the statistics options. There's a few things we're going to want to have selected here. We're going to have, under regression coefficients, estimates in confidence intervals. This is going to be useful if we need to write up this. We'll need the confidence intervals and the estimates. We'd like the model fit, the descriptives, and the collinearity diagnostics. We're going to be doing something else with residuals, so I'll come back to that in a second. Hit continue. We're going to go into plots. I'm not going to do any of these options here. I'm just going to select the histograms and the normal probability plot. We're going to make another residual plot here in a second based on something under the save option. So just have histograms and normal probability plot. Under the save, what we're going to select is the unstandardized predicted values and the unstandardized residuals. What this is going to allow us to do is create that plot, the fitted by residuals plot, which you might remember from the application that's online. This is going to help us here. As you can see, there's a lot of other things that we could save. So by no means are the things that we're learning in this course exhaustive, but we're getting some of the basics under our belt so that we'll be able to do multiple linear regression diagnostics testing. So again, we're going to have the predicted unstandardized and the residuals unstandardized, and we're going to hit continue. And what this is going to do, anytime you click something under the save option, it's going to create a new column in your data set where each ID or each observation is going to get both the residual from the model and the fitted value from the model. Under options, all of this should be default, but you'll want to make sure that you have all of this selected. Right here, this is going to assure us that we have, by including the constant in the equation, we're going to ensure that we get an intercept in our model. And then nothing under the style or the bootstrap. So once we're done with that, we're going to click OK. And I'm going to drag over my results, and you can see we first end up with our descriptive statistics, our correlation matrix, which could be useful in looking at. Again, before we would do our multiple linear regression, we do want to make sure we've explored this data thoroughly. We've gone through, looked at each variable, made sure that there aren't any potential outliers. Again, the way you assess an outlier is generally going to be based on you observe it through a plot or a table, and then you're going to go and investigate that point in your data and determine if maybe that point or that piece of data was collected incorrectly. Otherwise, you really should question excluding it from your data set. Whatever you choose to do, make sure that if you're writing up these results, you be transparent in your manuscript about exactly what you have excluded from your original data. Again, as a statistician, generally I don't include or don't recommend excluding residuals or excluding outliers. But some of the times, if the point is influential, it's causing the regression to go completely out of whack. It may be useful to exclude it, or to at least run the regression with it and then run it without it and compare the results of the estimates. That's usually what I'll do. To be honest with you, most of the time, doing this in practice, when you go through and you do that sensitivity analysis of excluding the potential outliers and then fitting the normal model, including those outliers, generally the results don't always change that much. If you have a small sample set or sample size, it could be an issue. But in general, again, the best rule of thumb when removing outliers is that you want to have a good reason that potential observation was incorrectly collected. So the correlation, the descriptives are all going to help you assess this data before you go on and interpret the results. The next potential variable or thing of interest here under the results in SPSS is our model summary. Probably going to be interested in something like the R squared. So this is the percent variation in the response that is explained by our variables that are in our model, which is 71%. The ANOVA result is going to tell us whether or not, again, our full model, the model that contains all of our variables that we just entered, is better than just the intercept-only model. So again, that's not really hard to do, to make a model that's better than just the intercept only, and therefore most of the time you're going to get this result to be significant. And it's not generally the most useful result. Usually people are interested in what are the estimated effects from the model, and whether those estimated effects are statistically different from zero or not. And that's where we get our next results, is under this coefficients table. So we can see we have our unstandardized coefficients, which are right here. These are those betas that are in the models that we write out. So our beta 0, for instance, is 2.342. Our beta 1, that's associated with baseline hemoglobin, is 0.04. Our beta 2 is estimated to be negative 0.004. Our beta 3 for age is going to be negative 0.020. And water is 0.004. Now, all of these seem very close to zero, but remember the units that we're dealing with. Water was in liters, age is in years, weight gain is in kilograms, hemoglobin, again, based on a variable that has a very small unit to it. So even though it appears to be small, we want to assess it in terms of how much variability we expect to see in that. So that's where the standard error comes in. Think of it as a type of standard deviation for each beta. How much variation does each beta have attached to it? If we're really confident, the data is very confident in that estimate, then the standard error is going to be very small. Again, this is assuming that your model has been correctly specified, that you've met your assumptions. If you've not met your assumptions, if your model's not specified correctly, your standard errors could be completely out of line with reality. So again, that's where the diagnostic tests are going to come back to, is telling us whether or not these standard errors are really trustworthy or not. But I'll go on here. Again, so we have our betas, we have how much variability we expect in those betas, that's the standard errors. So even though this is small, the effect of, say, age is small, we don't expect it to wiggle that much around that, right? The standard error is quite small compared to the actual estimate. And so that's why, again, it's the p-value here, the significance, the p-value, again, that's what this is pretty small. It means that even though this is small, we don't expect this to change that much compared to the standard error. And so we're pretty confident that it's not zero. And that's why we got our significance here equal to 0.025. And our confidence interval here, 95% confidence interval about what this estimate is. In a paper, you'd probably be interested in reporting the beta, the confidence interval for the beta, as well as the p-value. Another thing that we're going to get to later, probably in another video dealing with diagnostic test, is variable inflation factors, which has to do with whether or not these variables are correlated with one another. Generally, we want these to be less than 10, but really anything out of the bounds of 3, 4, or 5, you probably need to be potentially getting worried that maybe you have some variables that are too correlated with one another. Again, that's going to be called multi-collinearity, and we're going to touch on that in a later video. In terms of our diagnostic plots, we have, again, our histogram of residuals, which is right here. Again, we want this to be looking kind of normally distributed, and it generally does. Our QQ plot, we want these to fall in line, and you've seen other examples where the fit, the model's not correctly specified, the mean structure is not correct, maybe there's some curvature going on, and this QQ plot would really kind of bend off at the ends. We're not really seeing that here. Again, we have a lot of data, so even if there was some curvature, that data might overwhelm that curvature if it's slight. If it's pretty drastic, this QQ plot's going to do a good job at picking it up. Now, there's one other plot I want to do. It's our fitted versus our residuals plot, and I want to make sure we get that in here. And by default in SPSS, you're not going to be able to do it by just clicking a button. But remember that saved option that I selected. So I saved both the predicted values and the residuals. And what I'd like to do is make a scatter plot of the fitted values, again, that's the predicted, against, on the y-axis, the residuals. So let's do that. So I'm going to go to Graph, I'm going to go to Chart Builder. And again, with this, we're looking for a kind of random scatter of points. So I'm going to go to Scatter. I'm going to pull in my scatter plot here. I'm going to go down here. Can't see this, but if I drag this over, I can get my predicted on my x-axis and my residuals on my y-axis, and then I'm going to hit OK. Now, you can see this doesn't really look like a random scattering of points. All of this data over here, and I'm going to try to walk you through this quickly, what all of these points are over here are all those zeros for water. That's why they're all over here. Okay, so you might want to ask yourself, again, whether or not, really having one model for the zero water folks and then all the other water folks is really appropriate. Maybe it's really not. If these all look like a random set of points and these both look like a random set of points, I might be okay with having one model that for just the zero folks and just the other folks. But we really don't have that here. And while these look to be random in some sense, at least across here, there definitely seems to be a pattern here for these predicted values. And as you can see, as the predicted value goes up, our residual gets smaller in general. And that's what you see this line here to be. That's really not great. Generally, that may mean that we have some curvature in our data, but it's probably because we really have two sets of people here. Those that didn't consume any tap water and everybody else. We probably should make two models to really assess this data correctly. That's it for now. So if you have any questions, you can shoot me an email. If not, I'll be back with another video here shortly. So, thanks.